So Stefan will present us the next answers or giving us new opportunities for questions. So therefore, thank you for your second talk today.
Okay. Yes. So now I want to go a little bit more into research that we were doing, and then of course we can have a bit of a Q&A session again afterwards. So just a bit as a reminder. So maybe the vision of what we want to achieve is to do this kind of stuff. That's of course credit to Boston Dynamics, very impressive work. But what we wanted to do is that it really works in all kinds of environment with all kinds of tasks, ideally. So I want to move more into the top right corner of this graph that I've shown in the beginning. And I think the key to that is to have the right representations, spatial representations, that we can achieve that. So we're trying to now find these kind of representations so that you would have, dense representations, you would have things like individual instances, semantic understanding, understanding of people. So I'll be talking about some of the research that we have done into this direction to really cope with new environments as well, infer these kind of quantities, and then use them as a basis for action. So one of the things that I didn't quite get to just before was dense mapping. So dense mapping is a key to a lot of this stuff. We have done a lot of work in terms of volumetric mapping, where you have implicit representations of surfaces. So for instance, TSDF, truncated signed distance fields, where basically you have the zero crossing of such a function that now defines a surface. And it's signed because it's positive here in front of the surface and negative behind. Now, once you're dealing with these kind of volumetric representations, one of the bigger sort of practical questions is how can you make this efficient enough that you can deal with it computationally and memory-wise. So here's just some alternatives of what you can do. You can use things like hash tables to only store values in 3D where actually there is something to store. Or also we have invested quite a bit of time in using octrees. None of this is really a new idea, but actually if you want to make things work even with today's state-of-the-art computers, you need to think about these things. So with octrees you use this idea of always subdividing a block, and then maybe you have a dense kind of a block at the leaf level of your tree, and you can use this kind of representation quite efficiently. Another advantage of this kind of hierarchical representation is actually that you can now link it to sensor resolution, so that when you're far away from something, say you have a depth camera, you're observing something, well, say close first, right? Then you can maybe have a high resolution at which you store the data, the map data, and then as it moves away, you don't need that anymore. You only want to access things at a coarser resolution. So we have this kind of idea of adaptive and multi-resolution maps that chooses always the right level of detail in order to be efficient and to also avoid aliasing artifacts. So this is actually also, this has been released recently also as an open source library that we can do what is here, occupancy mapping. So we have, in some sense, a bit similar to TSDF, except that we now really store the full free space here. So whatever is blue, I can maybe repeat this here. Whatever is blue has actually been observed to be free space. So it was in front of the camera when you have observed depth behind the camera. And you can use this kind of adaptive resolution idea to really store efficiently very big blocks of data in free space where there's not much interesting happening. And then you can still resolve all the details of the, say, walls and obstacles and so on where needed at, say, centimeter resolution. And you can use that for path planning now, right? So we can really use things like RRT star or whatever in a very fast way in these kind of maps. So this is the kind of backbone of our drone navigation stack. So here maybe just to illustrate a bit how this actually works in practice when you now reconstruct the map. So this is mapping. We assume, as I mentioned before, that the poses are given. And now you're kind of constantly trying to prune the free space and make it kind of very big chunks of space here that you don't have to represent in any kind of detail, but at the frontiers of what you observe and at the surfaces that you see, you can still have high resolution, and then you have sort of both the details as well as the efficiency in these maps. And you can also then kind of propagate this information up in the tree, and you can do things like hierarchical free space queries with it. So you will have at the node of the tree, you'll have the information, aggregated information of what's going on with the children and grandchildren and so on underneath. So this enables us to be quite efficient in planning in the end. Okay, so now as a first example, I was of course going to talk about learning as well. The first maybe quite simple example of how learning can be very useful if you just do something like dense mapping, as I've just shown, is that very often we have our sensors that are somewhat incomplete, right? We have depth cameras, you've all worked with depth cameras, things that are too far away, there's some kind of shadowing, maybe you have the sun shining, and you will have holes in your depth map, right? At the same time, you have an image here, which is an RGB image, is always kind of complete by definition, right? So how about trying to learn how to fill in the gaps here? It's a classical learning problem. And it works really well. It's kind of a simple idea, works really well. What we can also do is we can jointly learn, just with the negative log likelihood training loss here, the uncertainty as well. So we can also get an estimate of how uncertain the network actually is about the depth that it is completing here. And then that integrates into the probabilistic mapping framework that we have, right? So in the occupancy mapping. And immediately you get much more complete here free space information, also quantifiably. Now this is super important if you want your drone to be able to fly around, right? If you have your holes in your depth map, you don't discover free space, you cannot safely fly there. So here's also a practical example of that. So that's one thing I wanted to mention about dense mapping. The other thing is that this idea of mapping, say, given the poses, is kind of not very scalable, right? So if you're using, say, a visual inertial SLAM system, you will always have drift in that SLAM system. We have talked about it before. You come back to a starting point, and if you're now just naively assuming that the poses are given and you integrate your depth into the map, you're going to make a hell of a mess of the map, right? This is an actual problem. You can't assume that the poses are given. They're going to be worse and worse over time, so we have to do something about it. And it's just a kind of simple standard approach is that instead of having just one global map, you will have submaps, and the submaps are anchored to the keyframes here, right? So you'll have kind of one submap per these keyframes, and now when you have a loop closure here, you're trying to deform this pose graph, and the map is deforming with it in the sense that the individual submaps are being aligned together with the keyframes that you have aligned, and you have mitigated this inconsistency. Now the idea is that the inconsistencies are really small from one map to the next, and then if you do these deformations, it's not going to really locally affect the map too much. So that's an important practical thing of taking these things out of the labs, and this is just some stuff here that we have done very recently. We have this project where we have to fly around drones in the forest fast, and this is now exactly the idea here, that we can integrate these maps, we can have these submaps, and therefore it's a scalable solution that we can actually fly through large forests, and we can come back to the beginning, and we can resolve these kind of inconsistencies. So here the green stuff is the kind of free space in the current submap. So this is kind of communicated also to the operator that this is safe to fly to. The other thing that we do is also here we're actually using learning. Instead of using the depth maps directly from the sensor, we're using learned stereo depth, deep stereo kind of approach. Again, here the idea is that it's actually giving us a lot more complete maps, depth maps that immediately give us the full free space information such that we can safely fly around. Okay. So stereo matching, right? That's one of these things I mentioned before. I think this is, to a large extent, is a learning process. What is the correspondence between left and right? Who tells you that? That's where I think these approaches, deep learning approaches, work really well. Now we can also close the loop, and this is a very new result just from a few days ago. We can actually really get the drone to fly around in the forest. And we still have to do a bit of a stop and go motion, mostly for safety reasons, because we want to always verify that what has been planned in these submaps is actually really safe. So far we didn't have to intervene. We have also not broken a drone, but it's somewhat surprisingly difficult to fly around in a forest, especially at higher speeds. So yeah, so it's visual inertial SLAM, it's doing these submaps, and then it's doing planning in these submaps. Okay. Now one more thing that I haven't talked about before is that you can also do dense tracking. You can also use, instead of sparse approaches I was talking a lot about. Is a question? Sorry. Yes.
I wanted to ask whether or not we're computing everything on board, or
yes, that's. Thanks for pointing that out. Of course, we're computing everything on board. So this is a big part of the challenge, right? Yes, and it's not simulation. So we have a quite limited processing power, but of course a lot has also happened. So it's using the newest Jetson, the Orion actually here. So we can run something at I think 5 or 6 hertz or so. We can run the neural network inference for the depth. And then we do integration into a map. Of course, we make some compromises in terms of resolution. We don't need to necessarily have all the finest details represented, but yeah, that these are real challenges. Yeah. Any more questions? Yeah.
Yeah, so one thing I could notice is like all these trees are of course static, but if there's an environment where there's swaying of leaves which are nearby, is there any experience you could share where you had flown your drone where there are dynamic obstacles which are
yes,
not
so
static trees?
this is a good point. I didn't really talk about it, but this is of course like one of the big challenges that we are facing, and we have actually seen it that, for instance, you take off, you're blowing around leaves, and it kind of messes up your map because you have all of these leaves in there that are moving around. Or you then don't see the stuff that actually is there because it's just been moved in front of the drone. Now, luckily, these things that tend to be the most dynamic are also not the ones that are going to crash the drone, so it can actually handle some leaves or even some grass or so a little bit. The sort of little branches here are more of a problem. If they actually are moving substantially because of more wind than what we had here, then this is a real challenge. The thing is, this is a 4-year or 3.5-year project. We are 1 year in, so we have the second and the third year to also think about representations that account for dynamics, to perhaps think about also learning-based approaches to avoid moving stuff in front of the camera. Yeah.
Thanks.
Okay. All right. So then maybe I'll move to just one more little bit of theory thing here that I haven't talked about, which is dense tracking. We can also try to align cameras with dense geometry. So far I've mostly talked about sparse. So what we do is ICP, for instance, with the depth camera, also with LiDARs, to try and align the back projected measurements, the dense measurements here, with, say, the projections in a keyframe. Or we can also do photometric alignment, where the idea is that the corresponding pixels here in a keyframe from the past and the live frame, they should have the same color, right? So that's the idea in dense tracking, that you should have consistent depth measurements relative to the dense geometry, or it should also have consistent color, effectively, or brightness. So we can use some of these ideas now also in some more recent work that we have done in terms of actually trying to now really move towards object level understanding, object level mapping. So in this work, we are trying to localize the camera, reconstruct the static world, and at the same time also segmenting the world into semantic objects and also track moving objects while we also reconstruct them. So it's kind of like maybe the hardest possible problem. And you see there are still some artifacts in this thing, but we want to see how far we can go with it. And of course, here now we are leveraging, well, in this case, actually 2D object instance segmentation, and then that allows us to bootstrap the individual maps. And why I was showing the dense tracking bit is exactly because we can now use these dense tracking ideas to then, well, not only track the camera relative to the static environment, but also to after having tracked the camera, then track the individual objects' motions, right? Also, this kind of idea of consistency, dense depth consistency as well as photometric consistency helps us identify which objects are moving in the first place. So assuming you have found the camera motion, you can then look at every individual object. Is it consistent in terms of geometry and color? And then if not, you have to assume that it's perhaps moving, and you can use the same kind of residual minimization to track the object's motion relative to that. So that's been the idea here, and then we use integration of the depth measurements from depth camera into TSDF. So this works somewhat, but as you have seen, there were some artifacts, and a big part, I think, of these artifacts that there are is due to the fact that once your objects are moving, your color consistency assumption is really very wrong, right? You can maybe get away with it in a static environment, assuming a Lambertian scene, but once you are actually changing the orientation, well, mostly the orientation, but also the location, I guess, of objects, inevitably the shading will change. And so this is kind of a broken idea in some sense. So what we've invested some time in and is again leveraging learning now for this part, and to instead of trying to align what are two images here that have very different illumination directly at the level of colors, to actually try and learn features that are somewhat invariant to these kind of changes, along with also some kind of a confidence map associated with it. And then this allows us to formulate a somewhat probabilistic photometric error. Well, it's not really photometric, maybe we can call it feature metric, because the only difference here is now that you don't use the intensities directly, you use learned features from a convolutional neural network in this alignment process. And you do the weighting with the inverse of the variance in a sort of similarly probabilistic way as we've seen before. And then you can put this into a fully differentiable Gauss-Newton kind of idea, where you have now these feature maps that are coming into an encoder, or the images here first that are coming into an encoder and produce these feature maps and the uncertainty maps. And you can then kind of, you keep downsampling, you have lower resolution maps. And ultimately, and that's also kind of important, downsample enough, you can feed this through a fully connected neural network here in the end to come up with an initial guess of what the relative pose is in between here. Now, this initial guess, that's kind of important, is not very accurate. That's maybe something that's also part of learning, right? That just some regression problem here is not super accurate, but it is accurate enough to then kind of go back in a coarse-to-fine way through these Gauss-Newton optimization steps. So then you basically keep refining the initial guess here, increasing at the same time the resolution, such that ultimately your finest resolution features match very well, right? So that's really a very robust, dense tracking framework that you can get like this, kind of leveraging both sides, right? So we have still Gauss-Newton, we still use this idea of probabilistic alignment here, but this is a differentiable process. So actually we can now learn this whole thing. Well, you still run this at inference time, these Gauss-Newton steps, right? But you're learning the features that are generated to facilitate this process using ground truth supervision here. So this then works very well, as I promised. So we use a keyframe and then try to align this keyframe to a live frame that we disturb quite heavily. And if you compare this to some baseline approaches that haven't been, of course, trained like that, this works really quite well to align these two together. Okay. Now, I was talking about trying to improve the tracking with learning, but we can also tackle mapping, right? So far, I've only talked about integrating sensor measurements, not so much about anything else, but we know an awful lot about the scenes around us, right? So how about leveraging some kind of prior knowledge about the scenes to complement what we see by the sensors? Now, if you look at the problem of just doing TSDF fusion, you just integrate sensor measurements from a camera, assuming known poses. Initially, you might not see very much of this chair, right? You have very incomplete geometry, and then you integrate more frames. Here is 5, 10, and so on. And you see more and more, so ultimately you'll have a quite complete view. Now, the idea is, how about using 3D completion such that you always get the best kind of estimate of a complete, in this case, chair. So in the beginning, this will be maybe a little bit wrong, right? But it is a chair, right, somewhat. And importantly, it should be consistent with what you see. So some of the previously existing approaches here, they might give you a nice chair. They might see, oh, okay, this looks a bit like a chair, and give you a chair geometry. But what is important, I think, if you do robotics, is that you want this thing that you're completing to be consistent with what you also see. So this has been our approach here, to try and have this kind of conditional completion that stays true to the geometry where you have already observed it. And then as you observe more and more, you will just always get the sort of best complete estimate that is also consistent with what you see here, just from the TSDF fusion. And now you can put these kind of things directly into a whole object level pipeline, and you get quite robust tracking of these individual objects that are also complete. And that's, of course, then potentially super useful to do things like manipulation, for instance. So I wanted to briefly show that, a bit more recent work, where we can now actually use these ideas to grasp objects, even though you only see a very small part of it as kind of incomplete. We can have this kind of completion step in the loop to actually grasp these things very reliably. So this is not the sort of camera that is in the gripper. It's a third eye kind of view, and we have now this completion pipeline in the loop that also gives us actually some kind of confidence as part of this mapping and completion exercise, and then we can focus on grasping it in a way that we're quite confident to grasp it. So you see the initial reconstruction is really quite bad, right? So you would have trouble grasping it in a sort of more model-based way with just such a reconstruction. But if we run a learning-based completion in the loop, then we can very reliably pick these things up. This is the completion confidence that I've shown, and that is also part of the pipeline. Okay, so with that, I wanted to move to the sort of maybe highest level of our spatial AI pipeline, which also now includes people. So I think again here is an interesting, there's some interesting things you can do at the intersection of probabilistic estimation and learning to see how both the camera is moving as well as how simultaneously people are moving. I've seen some very interesting demos yesterday about reconstruction of people's motion, and I guess here what we're trying to do is to take this also into a domain where the camera is moving at the same time. So that's in that sense a bit a more like a harder problem to try and do, that we had to go out of our way to make that work. So now you see how the camera is here moving as well, right? And we want to reconstruct the human in a sort of static frame, such that you can then also, maybe use that in your planning framework, or you can maybe extract the motion of the human to learn from that, while you have observed the human from a moving camera. So we're using image-based detection and human posture and shape estimation, but at the same time we're also combining that with a motion model that has been learned, so maybe addressing some of the questions before. If you're trying to model somehow how a human moves, you probably have lost already, right? So you need to have a learning-based dynamical model here for the people. And we can combine that together into actually, again, an optimization problem that now optimizes over reprojection errors, as well as taking into account the human motion model and the observations of the humans. I'll spare you some of the details here, but the idea is basically that you really need to include this motion model into the nonlinear least squares, in this case estimation problem, in order to get accurate estimates. If you're just kind of separating camera pose estimation and you're projecting out the human estimates, you get this kind of jittery baseline here. And if you're jointly trying to optimize this thing, you're getting much smoother, much more accurate estimates. Okay, so we have actually in most recent work also included that into both stereo as well as visual inertial. So just kind of augmented the whole problem, and then you get even more reliable results, as you may guess. So maybe I'll skip through to the results. So now we have, a left camera, right camera. We can now combine the reprojection error of static landmarks, the reprojection error of the human landmarks that are detected with a neural network, as well as inertial measurements for the camera motion, as well as the human dynamics model, and you get really quite accurate results with that. Okay, so the next thing I wanted to just briefly show is that we actually also invest quite a bit of time also, like the Bremen group here, in simulation, because I think it's super useful to generate training data, but also for training actual behaviors, for evaluating robot behaviors and SLAM systems and so on. So here we actually have an ongoing collaboration with this startup from China, Kujale, as well as more recently people from Intel and now Apple, like Vladimir Koltun, where we are leveraging from the startup these huge amounts of data that they actually have, well, not data, I should say scenes, and assets, such that we can realistically render them through Unreal and couple that with actual physics. So all of the objects here ideally are, can be manipulated, can be interacted with, and then you can use that, for instance, to deploy and train robots. So we did a little bit of sim to real transfer experiments with that already, and yeah, I guess this you could really do a lot of stuff with this kind of ideas. Load different robots in here. We're also working on a new kind of different kind of scenes, not just interior scenes like robot warehouse that you can then deploy your stuff in. So this is ongoing work. It's been online for a bit already. Again, it's still maybe a bit rough on the edges, some of it. So, but hopefully we can also develop a kind of community around that, such that it will be useful for all of us. Okay, so now maybe just for the last 5 minutes or so back to robots. So how can we now use these spatial AI representations on robots? So here's one where we quite tightly coupled now the spatial AI representation, which is actually an object level semantic map with a drone that is flying around. This here was in a simulation environment with the goal of doing exploration. So it's a completely unknown environment, and the goal is to try and reconstruct the environment fully, but also in a kind of directed way in terms of finding things. So we would have a specific category, object category, that the drone is trying to find. So it's not just an exploration problem of trying to reconstruct everything, but also with the specific goal of finding different objects. So with that, while also, of course, not flying into obstacles. So you're only allowed to plan actions into observed free space. And then we have also some part of the utility function that is taking into account how well the objects are already reconstructed, and with what level of detail to try and have high accuracy reconstructions that are coming out of it in the end. So as you see, this is now really very tightly interacting between spatial AI representation and the drone. So I just wanted to show also perhaps a few real examples. So we're also flying this in the drone lab just to show you. Again, it has to actually run on the drone. It's a bit of a challenge too, but that's perhaps why the map is not the highest resolution one here. But in the end, you still get a complete view of the free space, and you will find these objects, in this case, for some reason, keyboards and backpacks. So important to find. Okay. So to do these kind of things, we also need to actually do control. But I will skip through that a little bit. So far, the examples were kind of a bit simple with using linear model predictive control. So you have an attitude control drone here, and then you identify in a sort of gray box manner the closed loop dynamics as a linear system, and you can then use linear MPC around it. So that works quite well. But to do the more aggressive stuff that I've also shown before, we actually moved more towards identifying really the fully nonlinear dynamics, and then directly doing nonlinear MPC and directly trying to find the rotor speeds of the individual motors to perform these kind of maneuvers. And we can actually also augment that when trying to now interact with the environment. Part of why we try to understand the world around us is because we want to interact with it. And so as a first sort of example here, we put a delta arm onto our drone and now just augmented the cost for the model predictive controller by also trying to control, well, most of all actually trying to control the tip of this thing, that we can write something on a whiteboard. And so the way it works is that there's the end effector is actually penalized in terms of the lateral deviation from a nominal trajectory that we want to draw, and also to maintain a force if needed onto the whiteboard. And then, you know, this is what you get. I think it's still nice, these model predictive controllers, because you can keep the same. That's okay. You can keep the same controllers and you just adapt a little bit, and you automatically get these kind of behaviors. Now the delta arm is somewhat important because it can compensate for the deviations of the drone, right? It's kind of always deviating a little bit. And you can probably see where this is going towards. Okay, so this is correct. And then I think we did a couple more. Again, the idea is that it shouldn't just only work once. It should work several times. I should also say here, we're still using the motion tracking system. We still also told the drone exactly where the whiteboard was. So the next step, of course, would be to now bring it all together and have, say, visual inertial SLAM in the loop, have something, have some networks and 3D mapping in the loop that it would actually find itself where to fly to and draw something. So this is sort of 2D drawing. More recently, we have also done, let's say, 2.5D printing. So the same idea again, that we have a drone that is equipped now with also a delta arm to compensate for the drone motion and to try and print something here very accurately. So here we really need some sort of or centimeter level precision, let's say, for this to work. So this is some sort of cementitious material that we are printing, this kind of pattern. So the idea would be that these drones can actually, now maybe carry out some repairs or so, or build simple structures. So there's a big collaboration also, I have to say, with people from back at Imperial where I was before. A lot of people were working on that. A lot of drones crashed. So here is an example. So the reviewers asked us to print something bigger, and so we moved towards printing foam instead. One of the limitations, of course, you have with the drone is the weight, and so with foam it just works out better. Now what happens though is if you're building bigger structures, you can no longer just do some sort of feed-forward type planning, right? You can't just pre-compute the trajectory and then just print. You have to actually adapt to the real-world conditions, at least once you have printed the first or second layer or something. So now here we really had to put a spatial AI system back into the loop, okay? So actually you can see it here. We had this kind of reconstruction that we did at quite high resolution. There was actually a second drone even to come and fly around, but all automatic to come around and scan the whole thing with a depth camera, and then using our mapping pipeline, extract the geometry and adapt the successive layers of printing. So that was actually really needed here now to make this work. Okay. With that, I can come to the conclusions. So I hope I could convince you that there's still some value in doing SLAM and spatial AI, and actually that learning is really helping a lot for specifically inference of semantics, of course. I guess that's the obvious things, objects, people, but also things like data association over time. So this whole kind of feature metric errors that I've shown, as well as completion of geometry beyond what is visible. I think these are maybe some of the most obvious things where we can really leverage this kind of stuff. At the same time also that keeping a sort of modular architecture helps us for further integration and with robotic planning and control. And yeah, I guess my hope would be that some of these contributions can be also perhaps come into things like Michael's research when we are trying to deploy these robots in environments, everyday environments that have been previously unseen. I think this will be key to success, also commercial success, that you want to just get your robot to work at home, say, without having it seen before. So that's the goal here. Of course, big thanks to the team. Some people still at Imperial, but the bulk of it now at TUM, and the sponsors. And I should also say that we are hiring. I know some of you are perhaps finishing a PhD, and if you're looking, we're taking postdocs. So, okay, thank you very much. So then there's some more time for questions now.
Hello, thank you for nice presentations. I think the last session there was a lot of things that probably also need to see very details to understand. But I have some question regarding to body SLAM that you showed. It's really impressive. One of the things, for example, when you shows this body SLAM, so you consider that so you are watching from a camera that has some other sensors that to estimate the camera parameters for the body SLAM, right? So, but there's, I mean, like in my research, I cannot actually really get the